For Venus, it's especially dramatic. Venus' actual surface temperature is around 500 degrees Celsius, far above the boiling point of water, above the melting point of lead. This is a hot place. This calculation is way off for Venus in a way that it wasn't way off for Earth. What's going on? You do the calculation for Earth, we already know that the actual temperature is 33 degrees Celsius, 60 degrees Fahrenheit, warmer than it would be if we didn't account for the greenhouse effect. That's why the Earth's average temperature is 15 degrees Celsius. There's a 33 degrees Celsius greenhouse effect for Earth. Mars' actual temperature is actually, it's pretty close to the calculated temperature. It's certainly the closest of all of them. It's actually a little bit cooler, and there are some subtle effects going on here. I have included in these calculations the effect of reflection of sunlight from Earth and Mars in doing these calculations. I haven't included it for Venus. Venus, it turns out, is so cloudy that it reflects nearly all the sunlight coming onto it. And in fact, if you did a naive calculation that said somehow Venus reflects almost all the sunlight that comes onto it, but it doesn't have any atmosphere, an impossibility, but if you did that calculation, you would get a calculated temperature for Venus that's actually less than Earth's temperature because Venus reflects so much of its sunlight, but that's not what's happening. So what is going on here? Well, we already know what's going on for Earth. We know that Earth has about a 33 degrees Celsius natural greenhouse effect. That's the effect of the greenhouse gases in Earth's atmosphere blocking the outgoing infrared, or more subtly, absorbing the outgoing infrared, re-radiating it to the surface, and then the surface has to be warmer to get rid of that energy. What's going on Mars? Well, Mars has an atmosphere that is about 1% the density of Earth's. It's a very tenuous atmosphere. It's hardly any atmosphere at all, and it exerts essentially no greenhouse effect. And so Mars' climate is not significantly altered by a natural greenhouse effect on Mars. But you look at Venus. Venus's atmosphere is 100 times the density of Earth's. Huge amount of gas there. And it's 96% carbon dioxide, where Earth's, before humankind began filling with it, was about 280 parts per million. Venus's, if I said it in parts per million, would be 960,000 parts per million. 96% carbon dioxide, a very powerful greenhouse gas. Absent that, Venus's proximity to the sun would make it only mildly warmer than Earth. But it was enough mildly warmer that a lot of Venus's early surface water, we believe, evaporated, forming a water vapor-based strong greenhouse effect. And that caused a cascade of events that eventually resulted in a lot of carbon dioxide-based greenhouse effect in this strong carbon dioxide atmosphere. And Venus has what we call a runaway greenhouse effect. The greenhouse effect went wild. It built on itself through positive feedback mechanisms and brought Venus up to this impossibly inhospitable 500 degree Celsius temperature it now has. So Venus and Earth are two very similar planets. They're the same size, they're the same mass, they're approximately the same distance from their star, but that distance difference was enough to cause this runaway greenhouse effect to occur on Venus, and Venus now has this inhospitable temperature due to its 96% carbon dioxide atmosphere. We are pretty sure that a runaway greenhouse effect is impossible on Earth. So don't worry about the oceans boiling away here on Earth. That doesn't mean we shouldn't worry about greenhouse warming on Earth, but we are unlikely to go into that runaway state that Venus is in. So I would argue that our neighboring planets provide this natural experiment that confirms for us that the theory of the greenhouse effect is not some kludged together explanation to tell us what's happening on Earth, but it's kind of a universal principle that talks about planets that have atmospheres and describes the climates of those planets in terms of the composition of their atmosphere, and particularly the role that carbon dioxide plays in establishing the natural greenhouse effect in those planets. So that's the theory of the greenhouse effect. I introduced that in the last lecture, and this is the confirmation for the theory of the greenhouse effect. The basing on firm scientific principles, the correlation between Earth's temperature and its carbon dioxide concentration, and finally the tale of three planets, the greenhouse effects being very different on the three planets, Mars having almost none, Earth having a modest 33 degrees Celsius greenhouse effect, and Venus heating up by hundreds of degrees Celsius because of its greenhouse effect. Now let me pause and get a little bit here into philosophy of science, because isn't all this just a theory? And that phrase, just a theory, is being bandied about a lot these days to talk about scientific theories ranging from greenhouse warming to evolution. And I want to say a little bit about the phrase, just a theory. I think it's a misleading phrase, just a theory. What's a theory? In science, a theory is not just some hypothesis or vague idea someone puts out and says, maybe this is true. A theory in science is a coherent body of principles big underlying principles that behaves some body of scientific knowledge, or describes some body of scientific knowledge, and particularly describes many different instances. For example, the theory of the greenhouse effect describing what's going on 3 very different planets. That's an example of explaining a broad range of scientific phenomena. And these theories gain credibility as they're supported by evidence from observations, by laboratory experiments, and theories are rejected if physical reality conspires to disprove the theory. So established theories that have been around for a long time, have survived many, many, many tests, because every bit of scientific evidence has to corroborate the theory, or at least not contradict it. And if any bit comes along that contradicts it and can be repeatedly verified to contradict it, then the theory has to be replaced. There are many established theories that have survived these tests, and let me just give you a few examples. The theory of relativity in physics, which I describe in my course, Einstein's Relativity and the Quantum Revolution, my teaching company course, Modern Physics for Non-Scientists is the subtitle. That deals with phenomena ranging from the overall structure of the universe to astrophysical events to the functioning of the global positioning system. If we didn't understand Einstein's theory of relativity, we wouldn't be able to explain any of those diverse phenomena from the origin of the universe to the behavior of the global positioning system satellites. That's a remarkably solidly established theory. No reputable scientist doubts that relativity is part of a correct description of physical reality. That's a long established theory. In biology, the theory of evolution, which describes how species evolved through the evolutionary process, is a very well established, solid theory. In geology, and this is one of the newcomers to this list of big theories, the theory of plate tectonics, the idea that the continents move around over the surface of the Earth over time, driven by convective motions in the Earth's mantle. That's a relative newcomer, but that has formed a body of theory that then coherently describes a great many phenomena that we observe in the structure of our planet. And I would add to that set of big theories, not quite as big as evolution or relativity, or maybe even as plate tectonics, but nevertheless as well established and based on scientific principles and explaining a broad range of observed phenomena, is the theory of greenhouse effect that describes the fundamental principles that establish planetary climates. Now, I want to emphasize one other thing I said in the first lecture. A theory doesn't have to have explanations for absolutely everything in order to qualify as a solidly established body of evidence. Evolution doesn't describe every step in the evolution of every species. Plate tectonics doesn't describe absolutely everything that happened. We still don't know what goes on inside black holes because relativity doesn't answer that for us. We still don't understand every aspect of the climate system. What's the role of the carbon that's coming out of the soils or methane from plants? We don't understand all that. It doesn't matter in terms of the coherence and validity of the big picture idea. Climate scientists don't understand every detail of the climate system, but to point to a detail we don't understand is not to invalidate the theory of the greenhouse effect any more than to say, I don't know exactly how this monkey species evolved and I don't know exactly what's going on in this black hole, invalidate the long-established theories of relativity or evolution. So there we are with a solidly established understanding of what brings about planetary climates, and an essential key to that is the well-established and scientifically understood greenhouse effect.